Good morning, or good afternoon, and good evening, wherever you are. Thank you for joining us today for the IEEE Sensors Council webinar series. We recently initiated this webinar series as part of the IEEE Sensor Council's Optical Sensor Cluster to deliver expert talks on optical sensors topic. So this is a very great opportunity to learn about cutting edge developments and the technology in the optical sensors topic, and also establish potential collaboration opportunities if the research interest aligns. So I would like to welcome all of you today's webinar on fiber optic sensors applications in sorry, let me. So applications of distributed fiber optic sensing in oil and gas industry by Dr. Jyotsna Sharma from Louisiana State University. So this is a very emerging topic. Since last 2 decades, there has been lots of developments and also advancement in fiber optic sensing technology, but there is a gap between the lab research and the pilot scale demonstrations and make use to the industry to make an impact in the society. There are lots of applications in the energy industry. For example, wellbore integrity monitoring, oil and gas pipelines monitoring, gas leaks, structural integrity monitoring before catastrophic failures occurs. So this is very emerging topic. So today we are very fortunate to have with us Professor Jyotsna Sharma, faculty member from Louisiana State University in USA. So let me read bio of the Dr. Jyotsna Sharma. So Dr. Jyotsna Sharma holds an interdisciplinary appointment as an associate professor of petroleum engineering and an adjunct professor of electrical engineering at Louisiana State University in the USA. She also currently serves as a program director at the ARPA-E, that's Advanced Research Projects Agency Energy at the US Department of Energy. Her research has driven breakthrough innovations in fiber optic sensing technology, enhanced oil recovery, and machine learning applications for energy systems. A licensed professional engineer, Dr. Sharma holds five pending patents and has authored over 65 referred journal and conference publications. So prior to joining Louisiana State University, she was a subject matter expert at Chevron and leading production optimization projects across US and international assets in Indonesia, Venezuela, Canada, and Kuwait. Dr. Sharma began her career as a field engineer at Schlumberger in Canada. So thank you, Dr. Jyotsna Sharma, for agreeing to deliver this talk. I really appreciate your time. Before we begin, we will have a Q&A session at the end of the presentation. Please feel free to type your questions in the chat box at any time during the talk, or you can raise your hand at the end of the presentation. I will call you out and then you can ask questions. And also, this session is being recorded and will be made available through IEEE Sensors Council website and also YouTube channel as well. So once again, thank you for joining us today, and over to you, Dr. Jyotsna.
Thank you so much, Nagesh, for that introduction, and thanks everyone for joining today. So as Nagesh mentioned, I'll be talking about a variety of different applications of distributed fiber optic sensing for oil and gas industry. And this has been a game-changing sensing technique for, especially in energy production, because we are able to see so much more. And you'll see in the applications I'll share how this sensing technology provides so much information as compared to our traditional monitoring and gauges. Okay, so I'll just shut my camera just so that there is no, bandwidth issues as I go forward. So in my talk today, I'll start with a brief overview of how this works, just to get everyone on the same page. And then we'll look at a variety of different applications, starting with monitoring gas in wellbore. And we'll show a lot of data from the well. So this is all well scale study. We'll then look at pipeline leak detection, which is again a big area where fiber optic sensors have been very useful. Then we look at sand monitoring. Sand is also produced with oil and gas because a lot of hydrocarbons are in sandstone reservoirs. So when we produce oil and gas, sand is produced and it creates a lot of problems. So how can we monitor sand using these distributed sensors? We'll also look at a way to do distributed pressure sensing. And then finally, I'll share some field case study on downhole flow profiling, because flow profiling is one of the biggest application space for this technology, especially in oil and gas. And so all of these different aspects, different applications I'll share is from my research group. And throughout these different application areas, you'll see how we used machine learning, signal processing, data compression, data fusion, and numerical modeling. So all of those different techniques will be built into each of these case studies that I'll present. Okay, so let's look at how this technology works. So the idea is that we use optical fibers, as you can see in this picture, which is same fiber that is used for high-speed telecom applications. Here, although we are using it for sensing applications, so we send pulses of light from a laser unit. We call it an interrogator. And as the pulse of light travels through the fiber, some of the light is scattered back. And that back scattered light is then analyzed in the from the incident side. And the spectrum of that light gives us a lot of information about the different physical variables such as temperature, strain, and so on. Now, the biggest advantage of distributed fiber optic sensors versus the traditional gauges is the distributed sensing capability. Hence, we have distributed in the name, which means that here, for instance, in this picture, the entire fiber is acting as a sensor versus, say, if you have a point sensor or point gauge, which only provides us information at one location. So say if we have a 500 feet long fiber, we'll have 500 feet of sensing. So we have very high spatial resolution of data, and that gives us a much better understanding of the dynamic environment. So for instance, in a well bore, which can be very long, like thousands of feet long, especially in offshore wells, which are extremely long, in pipelines, which are again, you have hundreds to thousands of miles of pipeline crisscrossing the whole country. So you have very long pipelines, very long well bores. So a few discrete gauges will not give us the full understanding of the dynamics of the process. And that's where distributed sensors are a game changer, because the entire fiber is giving us this information. They do not require electronics along the optical path. So, all the electronics are in this interrogator unit, and there's no electricity passing through the fiber, which is again a very, very helpful thing, especially in downhole and offshore environments where any kind of, downhole electric sensor packs can be much more logistically challenging. So here there is no electricity going down, it's just light, and that makes things very, very easy. They are tolerant to high temperatures and pressures, again, very relevant for oil and gas applications, immunity to electromagnetic interference, and corrosion resistance. So many, many different benefits of using these sensors. So the light that is coming back, the backscattered light, has many different components. If you look at the spectrum, you have the Rayleigh, Brillouin, Raman. So these spectrums are what we analyze to then convert that into an interpretation of the temperature along the fiber, the strain, the acoustic measurements. So many different things can be analyzed using this spectrum. And then we can combine this to do other things. And that's what you'll see that, for instance, we combine DAS and DTS to do pressure measurement. And that is one of the application I'll show you. Another big advantage is that within the same cable, we can have multiple fibers inside it. So that enables us to do simultaneous measurement of DTS, DAS, and DSS. And that is very helpful, as you'll see, because that can eliminate some of the false positives. For instance, if you're looking at a leak at some point, if we just have temperature data or if we just have acoustic data, then there could be some false positives or false negatives, meaning like when there is no leak, we might see that there is some anomaly which might we interpret as leak. So having the ability to have multiple sensors within the same cable is very useful, because we are not increasing the footprint, the sensing footprint, because although this picture looks very magnified, but this typically a fiber is like quarter inch in diameter. So the fiber is, like hardly much footprint on your infrastructure, especially in wellbore. We don't want to put anything that will reduce our flow rates. So from that sense, this is not very intrusive to flow, within the wellbores and pipelines. Okay, so let me now jump into the first application. This was a project where we were looking at how we can do gas in riser monitoring. Now, the reason we are looking at this application is because one of the biggest safety hazards during drilling, and especially during offshore drilling, is a gas kick. What is a gas kick? So say if we are drilling a well, so in the schematic, you have an offshore platform, the drilling platform on the surface, and then at the sea bottom, at the sea floor, below that, we are trying to drill for the oil and gas deposit. During the drilling process, if the hydrocarbons enter the wellbore, so again, this is during the drilling, not during production, because during production, of course, we want the oil and gas to come into the wellbore. But if that happens during the drilling process, and as the hydrocarbons enter the wellbore, if we don't detect them, because these are highly flammable, they can travel up through the through our borehole and come to the surface and create, if it is not controlled in time, it can create an explosion, which we call a blowout. And in in an offshore setting, the pressures are very high. So even a small amount of hydrocarbon gas or hydrocarbon liquid can cause major incident. And sadly, this is what happened during the Deepwater Horizons blowout incident in 2010, when hydrocarbon gas entered the wellbore and it was not detected on time, and that created an explosion on the platform, and sadly many people lost their lives. So we wanted to come up with sensing technology that can help us to prevent this from happening. And one of the challenges with the current state of the art is that we typically have sensors on the wellhead and on the platform. But as you can even see in the schematic, the whole wellbore is very, very long. And even between the platform and the seafloor, we have what's called a riser, which can be thousands of feet long. So you have only sensors at few locations, in this case on the platform and wellhead, and then we don't have a good understanding of fluids in between. So thousands of feet of like basically blind spot that we have, and that is what creates a very dangerous situation, because many times these hydrocarbon gases are dissolved in the fluid. And because they are dissolved, they might just suddenly come out of the solution as the pressure is lower at lower depths. And now we have hardly any time, because maybe the gas is like 100 feet below our platform, and then it will quickly rise up, and we just don't have any time to control that, and it creates these type of accidents. So this is where we believe that fiber optic sensor can be a game-changing technology, because if I have a fiber optic sensor across this thousands of feet of riser, then if the gas comes in at any location along this riser, we can have an understanding of this anomaly, and we will have time to control this. Because again, as opposed to a point sensor, the fiber optic sensor gives us sensing along the entire fiber. So this is the hypothesis that we wanted to prove with our downhole test. So LSU has a very unique facility where we have 6 full-scale wellbores up to 5,000 feet deep. And these wellbores are on our campus, and this gives us a lot of, a unique capability to do tests in a wellbore, that we own. So here you can see the picture where we installed DAS and DTS on one of our existing wellbore. Again, DAS is distributed acoustic sensor, DTS is distributed temperature sensor. They were both within the same cable. So again, it's one cable that we are installing, which has multiple fibers inside it. This shows our well schematic. You can see that this well is 5,000 feet deep. So it's a full scale wellbore. The casing is 9 and 5/8 inches, and the fiber is installed on the tubing. So we are trying to mimic the riser with our well, and we want to show that if we have a fiber in this type of setup, if we have gas introduced, which is kind of mimicking a gas kick or that I just described, which can cause a blowout. If I have a gas kick entering my well, so we introduce that from the bottom of the tubing, then we can detect it with this fiber in the well. And one thing I would like to also mention is that during the drilling process, because again, this uh, safety hazard is during the drilling or sometimes also during the completion process. So we have typically drilling fluids which are mud. So if you think of a mud, it like literally looks like a mud. It's like a very thick fluid which has a bunch of clay, has lots of chemicals. So this is like a very viscous kind of fluid that we have in the wellbore. And if you compare that to some few gas bubbles, because when the gas first enters, it's just very few bubbles because it's like very high pressure. And then as it goes upwards, it can just expand. So even a very small amount of gas can very quickly expand as the pressure is much higher deep within the formation. And obviously, as it is at shallower depths, it's much lower. So imagine the challenge here where we are trying to detect a very small bubble while it is still deep below at because if we detect it very close to the platform, then we hardly have any time now to do any kind of control procedure. So we want to detect while it is still away from our platform deep below the formation. But it's a very noisy environment because you have mud and it's circulating at very high rates. When we are drilling a well, you have very high flow rates, hundreds of gallons per minute. You have drill cuttings and you have very loud, environment. And then you have mud as our uh, other fluid, which is going to disguise the gas signal. So there's a lot of challenges in terms of detecting it. But you can see that with the distributed fiber optic sensor and with the technologies we have developed in terms of denoising the data and doing a lot of frequency band energy extraction, you can see a very clear signal. So this is a 2D plot where depth is on the y-axis going up to 5,000 feet, which is the bottom of our well, and this is the time, and this is DAS data in the high frequency, and this is the low frequency. And you can see that we can clearly see this gas, and we have tried many different gases in our wellbore because different gases have different solubility in the mud. So we want to look at those effects. So here I'm just showing one data set with nitrogen, but many other gases were also we tested. So you can see the gas at any depth. So if say gas is at 3,000 feet, I will know exactly how big the slug is, so because that is an important consideration, how much gas is coming to the surface, because that dictates how we handle that gas. Because again, this is a flammable, highly flammable, hydrocarbon gas, typically it's methane. So how do we handle the amount of gas is dictated by how much it is. We also use it to calculate the velocity. So how quickly it is coming up. So we call it a frequency wave number transformation of the data. So again, there are a lot of different techniques, and I'll show some references where you can go and look at the details of the mathematical details of this transformation. But the key point is that just putting a fiber in the well is not going to give us the information. We have to take that data, do a lot of denoising, signal processing, in this case transformation, and you can also see here how we calculate the void fraction or the amount of gas using some of the inputs from this. So ultimately, we are trying to come up with some quantified numbers or quantified measurements from the fiber data. So just the fiber data alone is not enough. You need these algorithms to come to decision-making point, because how quickly the gas is coming up literally is a life and death question in this type of scenario. Because if it is coming at a rate where the time it will take for it to come from, say, at one location to the platform, if that much time is not enough to shut all the different valves and the blowout protector and so on, then the only option will be to basically evacuate the platform. So that time, how much time do I have and how much gas is coming up, it literally is the decision point for the rig crew and the rig operators. So this is what we get to using the fiber optic data. We also use distributed temperature sensor. In this case, we are looking at the gradient of that, and you can again see the rise of gas. Again, you can imagine this can be a kick which is coming up the riser, and we can clearly see how quickly it is rising up. We calculate the velocity, and this gives us this information. This is distributed strain sensor. In this case, you can see the signal is very weak, and this also highlights that in some cases having multiple sensors is a very useful thing, because compared to the distributed temperature signature, here the distributed strain signal is very, very weak because our strain fiber is not fully coupled with our fiber. It's a loose tube configuration, it's called. I can explain more if someone has a question. But again, having multiple fibers helps us to see another like DTS versus DSS. We can basically use different sensors and see which one shows the clearest signal. Now, data compression is a very important aspect, because these sensors uh, take measure data at high spatial resolution, high temporal resolution. We generate a lot of data. So for instance, in a 10-second DAS data in our well, so in our 5,000 feet well, is roughly 1 gigabyte. And this is just a 10-second data interval. And you can see this equation, which basically we use. So this is the spatial resolution, and our frequency of acquisition was 10 kilohertz. So 1 gigabyte in 10 seconds. Now imagine monitoring the well for several days, and it can even be sometimes like even longer than that. That is going to just generate enormous amount of data that we cannot handle. And what makes it worse is if you are in an offshore kind of environment, we have very limited resources. We don't have a supercomputer on the rig floor, and neither we have like some kind of ultra high speed internet and so on. We rely on satellite data links to send our data. So a lot of this processing, like this, becomes a bottleneck very quickly. You have this sensor, which is an awesome sensor giving so much data, which is great, but how do I actually analyze it quickly? So we have developed some methods. You can again look at this reference, these two references on how we compress our data. We also have some patterns on the data compression, because this then we can convert it from gigabyte to kilobytes. Now this has to be an intelligent data compression, because again, as you can imagine, this gas signal is very weak. So if I just chop off the data without actually thinking a lot about it, we might actually lose the signal of interest altogether. But that's where the intelligence, and by intelligence, like the key thing is the frequency that we analyze. So where is our gas frequency versus all the other things? And then we basically use some techniques for mask. We create mask with those frequencies and do frequency analysis to extract the data. In the end, so in our wellbore as well, we compress the data and then we send it to a cloud server for further processing, because again, on a platform we will not have the computational resources. And even if it is not an offshore, even in an onshore rig or onshore environment, these are remote places. Like, so we won't have like high speed computers sitting in the field, so we have to send the data somewhere to a control site or centralized location for the analysis. So the data compression is a key step here. And we also use machine learning to automate the process, because ultimately you may not have a fiber optic sensing expert who knows all this the signal processing and do all this in real time. So automating a lot of this so that the operators have an end-to-end solution is important. So in this case, let me just show you. So as the gas is coming in into our wellbore, our MATLAB code. So this is our MATLAB code running in the background, and it is automatically detecting the signal, as you can see here, and it is telling us the velocity as well without any human intervention. So this is fully automated. It's doing all the signal processing step, from the compression, denoising, and then signal detection. And this is where our vision is, to make this technology viable for an oil and gas company, or any company for that matter, to utilize it in the field application, because we do not have a fiber optic sensing expert available 24/7. And by the way, these drilling operations are 24/7. It's like it can be at the middle of night and whatever time. So automation is the key to make it faster and to make it viable for use, because as I mentioned, it's practically the best way to go forward with these sensors. Now, again, going on the same machine learning scheme, we had, because we did a lot of different experiments with different gases, different circulation rates, different wellbore fluids. We wanted to kind of create a repository so that when someone is testing things in the field, they can use some of our trained models and help in looking at those signals of interest in the field. So this is a work where we are trying to, so you can see, for instance, this is a convolutional autoencoded neural network that we used in this case. Of course, this is, it does not matter what type of network or what type of algorithm you're using. But in this case, this is a DAS data, and you can see that the gas signal is this diagonal line, but it is buried in a lot of noise. So one thing we have to, we need to appreciate is that the downhole environment is extremely noisy. There's a lot going on when we are drilling a well, when we are producing well, you have multiple fluids in the wellbore, they are circulating at high rates. There are drill cuttings, there is sand, there's very noisy signals which we have. And even in this case, with the gas being, these small bubbles have very weak signal as compared to others. So denoising of this to actually get the final gas signal, as you can see, this is our mask basically, which is what like an expert in fiber optic sensing will draw. So this is like our manual gas interpretation, and this is what the machine learning model basically predicts. So we are trying to teach how to get from here to here by doing all those signal processing steps. And that's where, the automation is going to be the way to make these sensors viable in the field. So we have done this on many different, different data sets, and it's not 100%. So this SSIM is just a structural similarity matrix. We just see how closely the prediction is matching our own interpretation. So it's not 100%, but it is pretty good for uh, for practical use. So I mentioned signal processing and denoising multiple times, and I cannot emphasize enough how important this is. Because imagine if you have a 10,000 feet wellbore, and the signal that is coming from like the 10,000 foot is actually much weaker because you have more optical losses the longer we go. Of course, it's, technology has evolved to a place where we don't have a lot of signal losses, but still we have signal losses. So denoising is very important. So in this case, for instance, the gas is, you can see it's completely opaque in this left hand picture where you have so many other things going on, whereas in the right hand side, in when we apply our mask in this low frequency domain, you can clearly see this gas signal. And because of the short time in this talk, I won't go into the details, the mathematical details, but you can reference this paper which I've provided here, where we go over many different denoising techniques that we have used. And it's not just for oil and gas industry. Wherever you are applying these sensors, you can use them to denoise the data. But it's a very important part. And doing frequency domain analysis is actually one of the key things that we do, and a lot of mathematical transforms. Because when you have a broadband type of noise, we can isolate it in the frequency domain a lot of times. And sometimes once you transform the data in mathematically, you can again isolate different types of signatures, and then you basically invert that. So that's kind of the high level way of doing this. We also use numerical models because ultimately we have this well in LSU, which is a certain temperature, some certain pressure and depth, but the offshore scenario could be very different. So we might have much higher pressures, much different. So ultimately, to do the for a company to utilize our data for their scenario, we want to develop these numerical models that are validated with fiber optic sensor data sets, so that we can basically upscale that to any different length and pressure scenarios. And again, if you compare this with a few pressure gauges. So typically in a well bore, we will have a few temperature and pressure of flow gauges in the well. So we only have very limited data to validate a lot of numerical models. Versus with a fiber optic sensor, for instance, you have in our case, for instance, we have 5,000 feet of high high spatial and high temporal resolution data. So in terms of validation of a numerical model, this is a very, very rich data set. And I would say that that is the biggest scope for any application in distributed sensors to validate the digital twins and come up with a verified model that can be then upscaled to any, any kind of operating condition. Leak monitoring is another big application of these sensors. So pipelines are very long and you can have leak at any location along the pipeline. And typically we have these pressure gauges at multiple locations, but if the leak is very small, the pressure gauge may not actually see the signal at all because the pressure change will be very small. And this is what we wanted to do in this particular research project, where we created a leak which is so small that our pressure gauge, which you can see in this picture, does not show any change in pressure because it's just so small. And here again, we wanted to show that a fiber optic sensor can be that game changer, or it can provide us that information that there is an anomaly, in this case a leak, which a gauge, which is the traditional way of monitoring leaks, is not going to tell us. So this is a setup in our lab at LSU, and you can see that the leak rate is as small as 0.03 gallons per minute. And that's what we wanted to show, that even a very small leak from a pinhole type of hole in the pipeline, we can still detect it with high fidelity. And once again, the signal to noise ratio and denoising is very important here because the pipeline has all other things going on around it as well. So ultimately, how do we know the signal is from a leak versus, like, like a cow walking near the pipe or something else, a car going through, or because the in this case, say if it is an acoustic sensor, it's going to sense everything in the environment. So just to give you an example, so DAS train, so this is just the raw data from the fiber. So you can basically see nothing. This is like completely, I don't know where the signal is, right? And the same, once we apply some mathematical transform to this data, and this is the frequency band energy, so this is mathematically how it's converted, you can see the signal just comes up. Like, so this is exactly the same data on left hand and right hand side, but this, we cannot see the signal here, it's basically buried. And here you can see the signal. So this is whenever we create a leak, and these are different leak rates in the pipe, and the leak is happening at 300 feet along the fiber. So this is a fiber wrapped on the pipe, which you can see here. But the takeaway message is that if I just go and buy a fiber and put it on whatever structure I'm monitoring, that alone is not going to give you all the answers. It's how you then take this data and process it such that we now see the useful information. And this mapping is where a lot of effort needs to be put in, because a lot of times the signal is there, but it's just not clear enough. There's a lot of noise and environmental parameters that have to be, removed to look at our signal of interest. And again, please look at, you can, if you're interested, you can look at this paper on exactly how this transformation was performed. Again, I have already mentioned the data size is an issue, and it is, in the pipeline, as you all know, pipelines are very long. So once again, the data compression is very important. And the good thing about our transform is that it not only, it clearly shows our signal of interest, but it also reduces the data size significantly. So even in this case, we are going from megabytes of data to kilobytes of data, which is, for a pipeline operator, yeah, kilobytes of data is very, very easy to do. So in this case, our pipeline is very small, but if these pipelines are very, very long, obviously, in most cases, it is a data that you can handle. We also use this to quantify the leak. So how much is the leak? And there's a quantification algorithm that we have developed both for pipeline and also for well bore. So if you have fiber in the well and you have these fluids which are flowing at different flow rates, how much is the flow rate? So you can see here the intensity that we extract from the fiber optic measurement is converted into a flow rate using our, basically, our algorithms, which you can see in this paper. So although I'm not going into the details of all these processing steps, because of the limited time, what I do want you to, appreciate is like the data can be actually used for many, many different things. So the same DAS information I can use for the leak detection, I can use it for measuring the flow, we can use it for measuring velocities, and that is where the beauty of these sensors are. You can do a lot with it and develop high fidelity numerical models that are very well validated with a dense data set. Even for pipeline detection, we do machine learning. In this case, for instance, we used a unit model. And again, this signal is very small. So we are trying to teach the machine learning model that even a small signal and with all the environmental background noise, can it detect it as a leak versus anything happening in the background. Now, one thing we wanted to do here is, say if I only have a DAS, so only distributed acoustic sensor, what is my confidence of detecting these very small leaks? And again, this very small meaning a pressure gauge will not detect a change in pressure, which is the current state of the art. We use pressure gauges typically in for detecting leak rates or presence of leak rather. So the goal is, can I just use DAS or can I just use DTS? So how much will be my false alarm if I only use one type of sensor versus if I use multiple types of sensors together. So if I do data fusion, because the same cable can have multiple fibers, as I mentioned, that's a big advantage of fiber optic sensors. So will I gain something by using multiple sensors or not? And that's what we wanted to test in this particular project. So we started with just using distributed acoustic sensor data, and we used this unit algorithm. And you can see that when we do a lot of signal processing, we do it in the frequency domain, and different when we apply different frequency filters, the accuracy of detecting the leak is different. So that is another thing where the frequencies of interest, like for leak in this case versus a car passing by or some other thing, will be very different. So there is an initial calibration stage where, depending on your pipe, the type of fiber, how it is installed on the pipe, all those can the depending on your configuration, you can do some initial calibration to identify which frequencies will be for your liquid flow, for your gas flow, and at least in a broad range. We may not be able to identify exactly that one frequency, but it will give us some idea. So without going into details, what we saw is, say if I only have distributed temperature sensor, then we saw that there could be many false positives. So you can see that here, the ground truth. So these are just segments of data. So this is DTS. So there is leak only in one location, but our machine learning model was showing that there are two leaks happening in the pipe, which is obviously not a good thing, because typically when we have a leak, we'll send an operator to go fix it or go look at it. So if you have a false positive, then it's just a waste of time for someone to go out there to check it out when in fact there's nothing going on. So this is not a good thing. We want to minimize false alarms for this. But because temperature can change, not just because the liquid is leaking out of a location, but it can change because of anything, like if there is a cloud cover, or if there is change in weather, change from day to night, temperature can change because of hundreds of different reasons. So DTS alone can give you some false indications that there is leak. So what we did was, we did a data fusion where we are not just using DTS but also DAS, because if the temperature is changing, for instance, because of the cloud, the DAS is not going to be affected at that location. Whereas if DAS is being affected because of a cow walking nearby, the DTS is not going to be affected because of that. So at a high level, that was the hypothesis. And that's what we saw, that the false alarm rate was significantly reduced when we do this data fusion. And because these cables enable us to do multiple sensors, this is a great way to actually make full use of these sensors by combining multiple types of sensors to reduce our uncertainty, because there's a lot of uncertainty even in wellbore, in pipelines, or any application in that case. there are uncertainty because these are a lot of interpretations, and someone can say, oh, I don't think that is happening. But once you have uh, independent measurements from different sensors, that builds our confidence that yes, this is the case. Pressure measurement is another very important thing, and we have developed an algorithm where we can take just the DAS and DTS as the input, only two inputs, and we utilize machine learning and signal processing to come up with a pressure output, because pressure is like a fundamental parameter or a variable that helps in controlling the process for safety, many different things, in not just in oil and gas, across almost every industrial process requires pressure measurement. So here, but pressure is often measured using a gauge which gives pressure at one point. But if you have a well bore, so if you have 5,000 feet of well, what if I want pressure everywhere? I want pressure at 100 feet, 200 feet, everywhere. And this is what we have tried to do, because if you have a fiber which is telling you DAS and DTS, can I combine this to give us pressure? So you can look at, we have a patent on this methodology and a paper in Nature, and you can look at how we have done it, and you can see that when we compare our predicted pressure, and we do that at different depths, because again, this is distributed pressure, meaning pressure at multiple locations simultaneously. You can see a very good agreement between our predicted pressure using this algorithm and the actual pressure which we measure using the gauge. So, and now the companies, many different companies, and there are researchers who are working in the hardware side. We have also developed some early prototype of actual hardware which can give us pressure, distributed pressure. In this case, this is an algorithmic approach where my hardware is just a DAS and DTS, which is commercially available today, whereas a distributed pressure sensor hardware is not commercially available today. So we can do it in both ways. Sand monitoring is another big challenge, or sand influx is a big challenge rather, in oil and gas, because you can see from this picture, like this is a pipe. Just look at the amount of sand. And because when we are drawing down or sucking in the oil and gas from our well, we also suck in these small sand particles which are from the formation or the reservoir. So a lot of this loose sand, as it goes through our pipe, it cuts through the pipes, it plugs up the pumps. It's just millions of dollars of operating expenses are go into the cleanup of these sand, and a lot of infrastructure is damaged because of the sand. Now, what we wanted to do is, can the fiber help us in looking at where the sand is coming from? Because a lot of times in the reservoir, there are certain zones where the sand is more unconsolidated, meaning it's loose. So there is a more probability of sand to get sucked in from that location. So we wanted to use fiber installed in the wellbore to help us identify those locations which are producing more sand, so that now we can do a targeted shut off of that location so that sand doesn't come in. We also wanted to use the fiber to look at the speed at which sand is traveling, because that dictates the erosion of our pipe, because these pipes are made of steel, but with a lot of sand, it gets eroded over time. And the higher that velocity of sand that is coming in, it's going to just cut through our pipe much faster. So that velocity is a key thing in terms of making sure that our pipeline can actually withstand those high flows of sand particles. So we wanted to do that with our fiber. And this was a project in collaboration with Shell, where they were specially interested in looking at for the offshore wells, because offshore reservoirs in Gulf of America are there is a lot of loose consolidated, unconsolidated sand. So there's a lot of sand production there. And especially when there are hurricanes and the offshore platforms are shut in for many days, as soon as the well start producing again, there is a big plugs of sand that come in. So sand is a major issue there. So we first wanted to do lab scale experimental modeling. So this is our pipe, 40 feet long pipe that this is in our LSU research lab, and we had fiber inside it, outside it. We wanted to see how easily the fiber can detect those sand signals. And again, you can look at all our algorithm in this paper, but we did a lot of spectrum, like waveform analysis, to come up with this frequency fingerprint of sand, because sand, is flowing with your oil, water, gas, but the sand is going to have a different frequency signature versus the other, and that's what we wanted to isolate. We also did analytical modeling to compare our data, the results from fiber optic sensor, for instance, the velocity value, with analytical model for validation, because validation is a very important thing with fiber, because there is a lot of interpretation involved, and we want to make sure that the velocity, for instance, which dictates how quickly my pipe will get eroded because of the sand, we need a good measurement of that velocity. So we validate it with analytical models. And again, we use machine learning to automate this, because this will help the operators to actually utilize this for their practical applications. We also do computational fluid dynamics modeling to basically upscale this data. So our pipe is only 40 feet long, but offshore well are thousands of feet long. So how can the company who wants to, Shell in this case, who are working with us, how do they use this data from our 40 feet long well bore, rather pipeline, to convert that into like a pressure and temperature they are operating at? So this is where, CFD modeling and basically, initial validation with modeling that can then be upscaled to different operating conditions can be very helpful. Of course, things are very different in the field, but this gives us some sense of how to, optimize our observations. But we also we did sand experiments in our well bore, because again, we are very fortunate at LSU to have our own well bores, where in this case, this is a this paper describes how we use DTS in this case to look at the migration of sand. And this final application is for flow profiling. This was a collaboration with a company who's working in California, and they were injecting steam in these horizontal wells. And the biggest application, I would say, of fiber optic sensors is in flow profiling right now, which is, relevant for injection, relevant for like hydraulic fracturing, where you have these multi-stage fractures. We need to know where the fluids are going, and we need to know where the fluids are getting produced from, because that these wells can be very long. You can have like 30, 40,000, feet of pipe, and we need to know where the fluids are. So in this case, they were injecting steam, but they were not sure whether this steam is going everywhere. And the reason why it's a steam injection is because the oil in this case is very viscous. So you can see 200,000 centipoise, right? So compare it to water, which is 1 centipoise, you can see this is almost like kind of like peanut butter kind of thing, right? So without heating it, it's not moving anywhere. So we have to introduce temperature to melt it, almost like melting of butter, and then the fluids flow. However, if I inject steam in this long lateral, but the steam just goes, shoots off in just in one location, then I'm not heating the full well bore. And steam is expensive, right? So you have to boil the water, generate this high pressure steam, compress it, inject it downhole. All of that is very expensive. So this expensive steam that I'm injecting downhole, I want it to heat all the reservoir. So the steam injection conformance is very important. And unfortunately, that was what was happening. So their steam that they were injecting was only going out from what we call the toe, which is like the end point of the well. And having the fiber, we created a numerical model for them, and then integrated the actual fiber optic data. So their well had a distributed temperature sensor. So we used it to validate our numerical model, and then come up with a steam profile, which showed us that the steam was going out preferentially. So once we know that steam is all leaking out at one location, then we can go back and put some inflow control valves, for example, so that the steam is uniformly across the whole well, because we want the steam to heat the whole reservoir, at least the formation of interest, rather than just leaking out at one location. So if you are interested, you can look at this paper where we integrate the data with a numerical simulator, because in oil and gas, using numerical simulators are like a bread and butter. We use it for everything from forecasting, from predictions and understanding the dynamics in the reservoir. So having fiber optic data gives us this opportunity to integrate that with our numerical models to make them more reliable when we predict, for instance, here how much production we'll get, how much steam is going at different locations. Okay, so with this, I'll stop here. I would definitely acknowledge all the students who have worked on these different projects, and I'm very grateful for their help and all their knowledge and expertise in these areas. And we acknowledge the funding support from a variety of different organizations, National Academy of Sciences, NSF, and our industry partners who have, for these different projects, we had different industry partners. So we thank all our collaborators, partners, funding support, and most of all our students. And with this, I'll be happy to answer any questions you may have.
Excellent. Yeah, thank you very much for the great talk, Jyotsna. Yeah, I think
Sure.
you done exceptional work. Yeah, in the data processing and pilot scale demonstrations. Yeah, if anyone have any questions, yeah, please go ahead. Okay, I see one question in the chat. Great talk, thank you. Please comment how much innovation in machine learning the existing manufacturers of distributed fiber optic sensors accepts their new products over the recent years. Example, Bandweaver, Halliburton, Sensoron, others. In your opinion, are they fast or slow?
Well, I think fast and slow is a relative thing. The problem is that because these sensor data can, as I mentioned, can become very overwhelming very quickly, and especially with these long pipelines, when we are doing flow monitoring, it's like terabytes of data, in no time. So that's where a lot of machine learning, signal processing goes into the data compression side. But intelligent data compression, so I think all the companies who are involved in fiber optic sensing are looking into that, because that's without that you cannot actually make these sensors practical for use, because if you have terabytes of data, then who can actually go through that in a timely manner, because we are doing real time monitoring, right? So if, for instance, if a gas kick is coming and it takes me 1 hour to analyze the data, then the blowout has already occurred by then, right? So literally we have seconds. I mean, in certain situations, of course, in some cases it's fine to do post processing, but in many of our applications, we want to look at things right away. Like if there is a leak, imagine an offshore pipeline leak. Within few minutes, the hydrocarbon basically go across so many miles because of the tides and because of the waves. So if we let the leak happen for even several hours, the damage, the contamination becomes huge, right? So how can we quickly process the data is a very important thing. So faster the better. And even actually, I have a project where we are using some quantum Fourier transform. So how can we accelerate that with quantum computation, which is a very promising technology. So I know researchers are doing it, including myself. Companies are doing it, and it's getting better. So we are getting faster, but there's still room for improvement.
Yeah, thank you. So we got one more question from Hani. Thank you for the interesting talk. What is the spatial resolution of the dash for the leak detection?
So what we used was 2.5 feet with what we had, and you can see that that's why it was helically wound. When we helically wind it, it gives us higher spatial resolution. But of course, in a long pipeline, you cannot have that much fiber. Typically, it will be just straight lateral type of configuration. But 2.5 feet was what we had, and our pipe is actually not very long. It's like only 20 feet. So that's where we had, you know, our data was a little bit blocky in the sense that it's just I'm seeing every 2.5 feet. There is a lot of innovation happening in increasing the spatial resolution, and I know Nagesh, you guys have done excellent work in that space as well. So yeah, the higher spatial resolution, the better. But again, if you think of, a 100,000 feet long pipeline, higher spatial resolution will give you an enormous amount of data too. So there is pros and cons of having, so it has to be right size for your application. So even for instance, if I have low spatial resolution, I can still, if we know kind of where the leak is happening, it will give us, then at least a shorter area to look at. So I think extremely high resolution is not always required, is will be my bottom line.
Yeah, yeah, good. Thank you. We got another question. Besides what's been covered in the talk, any other major challenges in R&D and apply this technology at scale?
X scale. Sorry.
Yeah, at scale.
At
Yeah,
scale. Oh, at
scaling
scale.
the technology. Yep.
Yeah. See, one of the biggest challenges, the fiber is along the, fiber only measures actually, and where we want to see like some maybe more innovation is how can we use it for mapping, right? For instance, like fiber is telling me what's happening along the fiber, but it's not just the well, we also have the reservoir. We need to know where fluids are coming from the reservoir away from the well, and how can we integrate fiber with all those like far field kind of things. So that is something where maybe fiber can be uh, integrated with other sensors. Other applications are distributed chemical sensing. Can we detect gas? There's a lot of even in my research group we are doing distributed chemical sensing with detecting gases. We are doing radiation monitoring. So if you have like nuclear power plants, and looks like we'll have a nuclear renaissance, so there'll be like lots of maybe nuclear power plants in the coming years. Then obviously for someone living near a power plant, the biggest thing is, oh, is there radiation, like am I getting radiated from that? But these large infrastructures with few radiation monitors, we may not get a good idea. So these fiber, we have developed in our group a gamma ray detector using the fiber. So 5,000 feet long fiber, the whole fiber acts as a gamma ray detector. So large area monitoring for chemical species, radiations, those are all, areas which will be picking up, I think, very quickly.
Yeah, yeah, that's good. And also, one of the challenges taking the technology to R&D, it meets the codes and standards of the industry. For example, pipeline, FIMSA has certain codes and standards. So any new technology need to meet their codes and standards. That's another one of the challenge. Yeah, great. And one more question from John. What are the biggest challenges for the fiber implementation moving forward?
I think cost is one of them. And then data processing. As you can see, if I just go today and buy a fiber, like that alone will cost, because these laser units, especially DAS, can be expensive. Although NETL is developing some low cost solutions, which is awesome, but typically it can be like $100,000, right? So even, but then our task is not finished yet. So if I go and buy it, put it on my whatever well, then you now need to know how to process the data. So there will be like resources, computational resources, personnel resources, all that is required. So cost starts to add up. And especially for smaller companies, that I think is a big hurdle. And that's where in my research, like being a professor, we want to develop solutions so that, people can use our work and just take it for free and then use it for their data processing. So hopefully that can be enabled. But like the value that we get for the price is also, the return of investment is a big upside. And I think it's the justification where it makes sense to put that cost to get what we need out of it. So cost is, I think, one of the biggest barriers in my experience, apart from the technical side. Obviously there's technical challenges, there's a whole different criteria, category, where you have environmental stuff. Like my signal might be, you might just say, oh, I don't see anything, like where's the leak? I just see like salt and pepper, like nothing, it's like waste of my money. But the point is, signal is there, we need to develop tools to actually extract that. So
Great. Yeah. Thank you. Yeah, we got few more questions coming up. Thank you for the nice talk. There are also developments looking into responsive coatings on the fiber optic cable combined with the distributed sensing techniques such as DSS and DTS, which require a lot of which requires a lot less data processing compared to the DAS. How do you look at these developments? Is this complementary or competing with the DAS technology?
I don't see it as competing as well. I think the better technologies we can develop, I think as an industry will benefit from those type of developments, because ultimately, like many of these things that we showed is, this helps in improving the safety of our operation, right? So if, for instance, when BP had that blowout incident, like I'm sure if there's a technology that some other company has developed, they won't say that, oh no, I'm not going to share that, you can have a blowout, I don't care. Like, no, like obviously not, right? So I think ultimately, the collaboration across industry, and actually oil and gas industry is doing a fantastic job in terms of collaborating with each other to develop these tools to make our industry safer and environmentally, more responsible. Because in a pipeline, nobody wants a pipeline in their backyard, right? If we, any of you, like, say, oh, let's put a oil pipeline in your yard, nobody would want it. Why? Because what if it leaks? What if it contaminates my soil, my water, so these technologies ultimately help us in addressing that first and foremost. And I think the innovation that you shared, yeah, that's awesome. And I think I don't see it as a competition as well. I think it's furthering our, it's improving our knowledge about how to use these sensors, and there's so much scope. So the more innovation, the better. Absolutely. And functionalized, these different layers, the coatings, these nanomaterials. Like I know Nagesh, you guys are doing a lot of work. In my research group, we are doing a lot of work. So that is the future, where
Yep.
these reactive type of coatings, they can give us the information about these chemicals in the environment.
Yep. Thank you. Yeah, we got one more question from Abhilash. Thanks for the presentation. We had two questions. First one, noise problems. Do you also consider optical noise sources from the laser? For example, relative intensity noise RIN at transmitter end, and the photoreactor noises such as short noise, dark current noise, and also flicker noise at receiver end. How can it be managed? And the noise cancellations. Do you also face challenges from optical echoes with the fiber system? How do you resolve it?
Yeah, so all those noise are, definitely impact our overall signal visibility. And we generally do like optical budget, noise budget, because ultimately if the signal that we are detecting, if it is below that noise budget, we cannot detect it. Like it's just there is a fundamental limitation. And given that this is an optoelectronic device, there is going to be a baseline noise because of, just from integrating these different components together. Of course, hardware companies are doing a lot of research and innovation to address these. I even have a project where we use like squeezed light. So this is quantum state of light where we are reducing the noise to the short noise level. But of course, like it's not ready for like field deployment yet. This is like we have a huge lab, bench scale setup in our lab, but I cannot yet take it to the fields. But at least from the research side, we are trying to minimize those different, noise sources, and all those noise, that was mentioned in the question are highly relevant. So it's a definitely hardware providers are looking into that, but to some extent we have to live with some noise. I think that's just, fundamental constraint of the equipment.
That's true. Yeah, because the system noise itself has a laser noise, rim noise, and then phase noise, and also yeah, that's true. If you use the quantum laser sources, like a two entanglement laser source, we can greatly reduce the short noise. So that's the
Right.
future research coming up. Okay, I think I've lost another question. Thank you for the amazing presentation. Is strain coupling an issue which affects your results, and how you try to maximize strain coupling?
Yeah, yeah. So at least in our case, when the coupling is very important. So what we have in our well, when we first installed it, the fiber for strain is loosely coupled. So it's basically just hanging. It's a loose tube type of configuration. So the fiber is not strain coupled with our well. And that's why the data that I showed for DSS was very noisy, very poor signal that we saw. And so that was obviously a learning that we should have not used a loose tube configuration. But yeah, how the fiber is installed, because ultimately, if there is no mechanical coupling, for strain, or in case of temperature, how it is monitoring the the environment, it ultimately comes down to where the signal is and where the fiber is. So that coupling plays a very important role, and even the fluid in between affects the coupling part. So say if you we have a dense fluid, or if you have a rarefied medium in between, then that coupling, because we are trying to monitor what's happening in the reservoir, that is also affected. So yeah, now there are only so many things we can do. So ultimately it comes down to, even with a low coupling, can I still see the signal? And a lot of times it comes to that, because we cannot have a perfect setup. Like, regardless of what we do, there will always be noise, there will always be signal which is weaker at the bottom of the well versus the top, because some light is going to be lost. Even if I use the best system out there, light will be, because it's scattering, so you will have some loss. So the signal quality is going to be an issue. But if we can develop techniques to still look at our data of interest, then that's where we can address some of those.
Yeah, great. Yeah, yeah. I got like Ellen saying, "Congrats, Jyotsna," and then V from GE. Thank you for the great presentation.
Thank you so much.
Yeah, thank you very much. It was great present. I think we don't have any further questions. Yeah, thank you very much, Jyotsna. Yeah, I really appreciate. And then yeah, have a great Good Friday and then happy weekend to all.
Thank you so much, everyone, for joining, and thanks so much, Nagesh, for
Yep.
this opportunity.
Thank you.
Right.
Yeah. Have a good
Alrighty,
bye.
bye.